Have you ever wondered what the absolute best way to do something is? Not just a good way, but the optimal way? Well, it turns out there's a powerful mathematical tool designed to answer that exact question. And that's what we're going to unlock today, the calculus of best.
I mean, just think about it for a second. Why do bees build their honeycombs with hexagons? Why not squares or circles? It's because bees are kind of like nature's perfect little engineers. You're looking at it right here. The hexagon is the most efficient shape, hands down. It lets them use the least amount of wax to store the most amount of honey. They're basically solving for best without even thinking about it.
And this isn't just some fun fact about bees. The great mathematician Leonhard Euler believed this was a fundamental principle of the entire universe. This idea that nature is constantly seeking a maximum or minimum really sets the grand stage for what we're talking about.
So this whole quest for the best possible outcome, it's not just some philosophical idea. It's a real, practical field of study with a formal name, and it's at the heart of solving countless real-world problems.
And that process is called optimization. At its core, it's about taking a real-world goal, translating it into a mathematical function, and then finding its highest or lowest point. Think of it like you're standing on a landscape, right? Are you trying to find the highest peak to get the most profit? That's finding a maximum. Or are you looking for the lowest valley to have the least cost? That's finding a minimum. Simple as that.
In this question, it pops up literally everywhere, whether we're conscious of it or not. I mean, every time you think about the most efficient route to work or the best way to invest your savings, your brain is doing a little optimization problem.
And the applications are just fascinating. Using optimization, we can figure out the ideal shape of a can to save on material. We can design spacecraft for maximum acceleration, which is absolutely crucial for safety. Calculus can even model the biology of a cough to maximize how much air you expel, or the way our blood vessels branch out to minimize the energy your heart uses to pump blood. It's incredible.
Okay, so when you hear about problems this complex, it can sound pretty daunting, right? But what's so amazing is that there's actually a systematic approach, a repeatable blueprint that works for all of them.
And here it is. This is the blueprint, a powerful three-step process. First, step one, you have to truly understand the problem. What's the goal? What are the rules you have to play by? Step two is to build a model. That just means creating the math function you want to either max out or minimize. And finally, in step three, you use the tools of calculus to find the optimum, that highest or lowest value. This blueprint turns a messy, real-world problem into a clean, solvable equation.
All right, theory is great, but let's make this real. Let's apply that blueprint to something you probably see every single day, a simple cylindrical can.
So here's the question we're trying to answer. We need our can to hold a specific amount, let's say 1,000 cubic centimeters, which is just a liter, but our goal is to use the least amount of metal possible. That means we need to minimize the can's surface area.
Now for step two, building the model. To do that, we have to really understand what a can is geometrically. And it's pretty cool. If you were to unroll a can, what would you get? You'd get two simple circles for the top and bottom, and a rectangle that forms the side. The total area of those three shapes is the can's surface area, and that's the number we want to make as small as possible.
Now, every optimization model has two key parts. First up, you have the constraint. This is the non-negotiable rule. For our can, the volume must be 1,000 cubic centimeters. No ifs, ands, or buts. This formula here just connects the can's radius, r, and its height, h, to that fixed volume.
And here's the second part, the goal. This is the function we're actually trying to optimize. For us, that's the surface area, the area of those two circles plus the area of that rectangle. Our mission is to find the dimensions that give this function its absolute lowest value. So, how do we find the answer? Well, this is where the magic of calculus comes in. We use our volume constraint to rewrite the surface area formula so it only depends on one thing, the can's radius. And if we plot all the possible surface areas for every possible radius, we get this U-shaped curve. Calculus gives us the tool to find the exact bottom of that curve, that single low point right there. That's our answer. That's our perfect can.
And get this, after all that math, calculus reveals a surprisingly simple and elegant answer. The most efficient can, the one that holds a set volume using the least possible material, is a can whose height is exactly equal to its diameter. It's as tall as it is wide, a perfect square profile. How cool is that?
Okay, so this whole problem-solving blueprint thing, it's way bigger than just making perfect cans. It's also a cornerstone of business and economics.
And this right here,
perfectly shows you just how versatile that blueprint is. On the left, our goal was to minimize material by finding the lowest point of the surface area function. But on the right, imagine a totally different goal. You want to maximize profit selling necklaces. You'd build a profit function and find its highest point. See? The goals are opposite, the functions are different, but the three-step blueprint for finding the solution is exactly the same.
And that's really why this is all so important. Optimization provides a logical framework for making the best possible decisions, whether that means minimizing waste in a factory or setting the perfect price to maximize revenue.
So when you really zoom out, you start to see that this quest for the best is this powerful thread that runs through, well, pretty much everything. Engineering, biology, business, even the fundamental laws of physics.
We started with bees instinctively minimizing the wax in their honeycomb. But this principle is everywhere. In physics, there's something called Fermat's principle, which says that a ray of light traveling between 2 points will always follow the path that takes the least amount of time. It seems like Euler was right all along. The universe is constantly solving for best.
So the big takeaway here is this powerful three-step blueprint for finding the optimal solution. It's like a new lens for looking at the world around you. Now that you have it, the question is, where are you going to see optimization at play in your world?